Welcome to EPG Pathshala lecture series on computer science. In this module, we will be discussing about association rule mining, how a priori algorithm may be used for deriving association rules. The learning objectives of this session will be to learn the working of a priori algorithm and then use a problem to understand the working of a priori algorithm. So, association rule analysis, here we are going to mine single dimensional Boolean association rules. Now, what do you mean by single dimensional Boolean association rules? When we talk about an association rule, on the LHS of a rule, you can have one or more attributes or one or more predicates for the purpose of determining the RHS. In case if you are going to involve a predicate, a single predicate or a single item for the purpose of predicting the RHS, then it is going to be a single dimensional association rule. And what about Boolean? Boolean here indicates either the presence or absence of an item or the truth or false associated to a predicate. So, ultimately we are going to predict association rules which are going to be single dimensional and Boolean in nature. In the previous session, we discussed about the basics related to mining association rules from voluminous transactional databases. So, from the session itself, we can recollect that for identifying association rules, you may require frequent item sets, that is finding the frequent item sets. What exactly is a frequent item set? When we recollect from our previous session, we can understand that any item set or set of items that satisfy minimum support or minimum support count will be treated as a frequent item set. For example, if you have a database of 4 transactions and assume an item in the database has occurred twice, the probability of occurrence of that item will be 2 divided by 4, since 2 is the number of events related to occurrence of item A and 4 is the total number of transactions. So, it is going to be 2 by 4, 1 by 2, which is 50%. Suppose if I fix the support to be 50%, then I will have to identify all those items that satisfy this minimum probability value. So, ultimately we are trying to identify such item sets that satisfy the minimum support count and we treat that to be the frequent item sets. The frequent item sets are then used for generating association rules. Now, what is the purpose for identifying frequent item sets? The item sets that are identified to be frequent may highlight some interesting patterns or features that is hidden in the transactional database. These patterns sometimes may highlight an association or a correlation or even a simple relationship between more than one item, and frequent items are the one that are only positive combinations and that do not report combinations which has lesser frequency in terms of occurrence. And frequent item set actually aims towards providing a summary of the data and the occurrence of such patterns in the given or the entire data set. Now, the task here is given a transactional database say D and with a minimum support say S, which will act as a threshold. The task here is to find the frequent item sets and the frequency of each set in the data collection. So, how you can state this is, we are going to count the number of times a combination of certain attributes that occur in our data set. If the count of this combination is above the minimum support, then we consider that to be a frequent item set. So, objective is to identify item sets that are frequent in nature. Now, you will have to recollect that the database D has many sets of transactions and contains multiple subsets of item that may be considered to be the universe set. Now, when you are generating item set, what may happen? Assume you have 5 items A till E. To start with, I can have single items A, B, C, D and E separately, then you can have combination of these items put together, which can be two dimensional items, that is in a set there will be exactly two items. For example, combination of A and B, combination of the product A and C, combination of the product A and D, combination of product A and E, and so on. As shown in this diagram, you can find single items when combined may provide two items together. So, the single items here put together can be treated as single item set. The two items over here put together can be considered as two item sets, and when you combine the two items together, that is two sets that contains two items, and among the two items one will be in common. For example, if you take the item set A B and the two item set A C, you can combine these two item sets by means of having a common item, that is A. Therefore, the new item set that will be generated comprises of three items A, B and C, and this three item will be treated as a three item set. Likewise, you can generate four item set, and at the maximum, since there are 5 items, individual items in the given transactional environment, you may end up with occurrence of all these 5 items A till E together and considered as say 5 item set. Now, when you take a look at this diagram, you will find these are the combination of item sets that may be generated. In the topmost end, you may have null set indicating none of the item occurring, and at the bottommost level you may find all the items occurring together as a single item set. So, the number of items and the combinations actually determines how complex will be an algorithm which is used for generating item sets and association between those item sets. Here, when you are having D items, then there would be 2 to the power of D possible item sets. So, in general, here in this scenario, if there are 5 items, so D will be equal to 5, then possible number of item sets that will be generated is defined by the equation 2 to the power of D, say 2 to the power of 5. So, that will be the number of total number of items that will be generated. Now, if this D is going to be large, yes, of course, it will be large. The reason is, when you take a look at many transactional environments, the number of products displayed in those environment or the number of entities that participate in such environments may be very, very large. For example, if you take Amazon, Amazon may work on say 1 crore products. So, now D will be equal to 1 crore. In such scenario, how many such possible combinations may come into picture is, it is 2 to the power of 1 crore. That will be the complexity associated with generating all item sets. Now, if this task is going to be so complex, how you can make use of this task into sensible and say a feasible one? For that, you should not look in for a support which sometimes is equal to 0, because it is not at all going to provide you any information. Sometimes you should not have a minimum support which is so less that all the items that is available in the transactional database will be considered as part of the item set. So, the summary that you are going to generate will be very large, and thus it will not be interesting. Now, the task here is, the ultimate task is, how are you going to set the value for minimum support? Sometimes if it is so large, what may happen is, none of the items may get selected. So, you will have to be very careful on fixing the value for minimum support. Now, when we understood that 2 to the power of D is the total number of items that may be generated for given D items, how you can identify what is essential and what is not essential? Please recollect the concept of frequent item sets, which we discussed in the previous session. As part of a priori algorithm, an item only when it is frequent will be considered for the purpose of generating a rule. So, when you are generating the various combinations of item sets, you will have to verify whether an item is frequent or not. In case if it is frequent, then it will be considered for analysis, else the infrequent item set will be ignored for the analysis. So, what happens is, during the process of generating all possible combinations of item sets, if you find a particular item, for example, here in this scenario AB is going to be infrequent, then all the other possible item sets that will be generated or involving AB will also be treated as infrequent. This is actually the working principle of a priori. So, a priori principle states, suppose if an item set is considered to be infrequent, then all its subsets will also be considered as infrequent. So, when you are generating the possible number of item sets, then you can identify some set of items which may not be frequent, and hence they may be ignored during the process of generating item sets. Now, let us once again recollect the steps involved in a priori algorithm, and after understanding the steps, let us take an example and then understand how frequent item sets may be identified using a priori algorithm. There are two steps involved or two phases involved in a priori algorithm. Phase 1 is join phase and phase 2 is prune phase. This we discussed in the previous session. Therefore, I will not in detail explain this, but I will give you an overview. Join step is generating candidate set. It is used for generating candidate set, and prune step is for eliminating the infrequent item sets. So, the candidate set here afterwards will be represented by the notation Ck, and the prune step or the phase will identify how many such candidates are not frequent, and those infrequent candidates will be eliminated. Consider this example. In this example, there are 4 transactions with transaction IDs 100, 200, 300 and 400 respectively. Let us take the first transaction 100. The first transaction 100 comprises of 3 items 1, 3 and 4. Similarly, 2, 3, 5 for the second transaction, 1, 2, 3, 5 for the third, and 2, 5 are the items as part of the fourth transaction. Now, our task is to identify what are the item sets that are frequent. Now, to generate frequent item set, the requirement is you need to set a threshold which is the minimum support. Assume for the given example, the minimum support count is equal to 2. What does it mean is, when you want to define any item set, kth item set to be frequent, then it must have a minimum frequency of occurrence which is equal to the minimum support. Now, as part of the a priori algorithm, the first step is generate all possible candidate set. Now, the a priori algorithm, given this transactional records, it will scan through the records and then identify all possible single item sets. So, now from the transaction database, the a priori algorithm is going to scan all these transactions and then list down all the unique item sets. So, first it scans the record 100. From record 100, it identifies 3 unique items 1, 3 and 4. Then when it scans through the second record, the algorithm will identify 2 and 5 as a unique item, since 3 has already occurred in transaction 100. Similarly, 300 and transaction 400 will be scanned. After scanning all these records, set of unique items will be generated. Now, for each and every unique item, you will have to identify what is the frequency of occurrence. From the given set of transactions, for item 1, if you count, you will find item 1 has occurred in transaction 100 and in transaction 300. Therefore, item 1 has occurred twice. So, the number 2 here indicates the occurrence frequency of item 1. Similarly, you will have to calculate the frequency of occurrence for item 2, 3 and 5, which are 3, 3 and 3 respectively. Now, you have generated the candidate items. Here item 4 has occurred only once. So, with the list of unique items 1, 2, 3, 4 and 5, when you take a look at it, except item 4, the rest of the items 1, 2, 3 and 5 have a minimum support value 2. Therefore, those 4 items alone satisfy the minimum support and hence will be treated as frequent item set. From the given candidate set, you are generating frequent item sets. So, candidate set here is represented by C1 and the frequent item set is represented by the rotation L1. Now, the frequent item set which is generated comprises of exactly one element in each and every set. Therefore, it will be treated as one frequent item set. In other words, all the sets in the table contains exactly one element or one item. Now, after completing one iteration, you will have to go for the second iteration. In the second iteration, you will have to identify what are the frequent items and then join these frequent items with itself. So, now comes the prune phase. So, earlier we were looking in for items that were not frequent and ignoring them. So, that is the pruning phase, and now the frequent item sets L1 from L1 set should be joined with itself. Now, when we join the items in L1 with itself, you will be generating item 1 comma 2, item 1 when combined with 3 you generate item 1 comma 3 and then item 1 comma 5, then item 2 comma 3, 2 comma 5 and finally item 3 comma 5. So, the possible 2 item sets, candidate 2 item sets are listed here and indicated by the notation C2 dash. Now, you will have to identify what is the frequency of occurrence for each and every of these 2 item sets. The item set 1 comma 3, when you scan through the database, you identify that it occurs in transaction 100 and in the transaction numbered 300. Therefore, the frequency of occurrence of item set 1 comma 3 will be equal to 2. Similarly, you will have to calculate for 2 comma 3, 2 comma 5, 1 comma 5, 1 comma 3 and so on. Having identified the frequency for each and every one of these 2 item set, candidate 2 item set, next you will have to apply the prune step. Here the prune step, you will have to verify which are those 2 item sets which are in as part of this candidate item set satisfy the minimum support. The item sets, 2 item set that satisfy the minimum support are listed here as part of L2 table. So, item 1 comma 3, item set comprising 2 comma 3, 2 comma 5 and 3 comma 5 are those items that satisfy the minimum support count. Therefore, only these 4 2 item sets will be considered as frequent 2 item sets. Once again, you will have to go for the third iteration. In the third iteration also, you will be performing a join and then prune operation. So, you will have to run this algorithm until you get the maximum possible combinations. Here the maximum possible combination will be identified by means of the maximum number of items which is part of a transaction. When you go through the original transaction input, you find transaction 300 comprises of maximum number of items, that is 4. So, put together you can generate an item set that comprises of at the maximum 4 items. When you go through this algorithm, the algorithm actually stops when there is no more further frequent item that may be generated or when there is no more candidate set that can be generated. Here, as part of the given example, the algorithm will come to an end when there is a 3 item set which is going to be frequent, because its support value is going to be equal to 2. Now, what happens is the algorithm will stop here and then it will list down what are the possible frequent item sets. So, when it is going to list down the possible frequent item set, it will list down the single frequent item set, 1 frequent item sets, the 2 frequent item sets and the 3 frequent item sets. As a result, what is that you can infer is, you can identify there are few items that has occurred often based on the minimum support. Now, what is that you can do with these frequent item sets? our main objective is to identify associations. When you want to deal on associations, then you do not require single item sets. Instead, you may require the rest of the items, that is 2 and more frequent item sets. So, from the 2 frequent item set, what is that you can infer is, in case if item 1 occurs, then there is a chance, fair chance for item 3 to occur in the same transaction. Similarly, in case if item 2 occurs, then there is higher chance for item 3 to occur in the same transaction. In reality, if it is going to be a shopping mall or a supermarket, I can say if a particular customer purchases item 2 or product 2, then there is good chance for the same person to purchase item 3. This is how it can be interpreted. So, the main objective here is to identify frequent and infrequent item sets and use the frequent item sets alone for the purpose of making decisions. Having understood a priori algorithm with an example, now let us understand what are the real challenges. The real challenges of a priori algorithm are counting and generating the item sets which are considered to be candidates. Now, what may be the real challenge? In case if D is very large, like 1 crore, then the total number of combinations of item sets which is going to be generated will be too high. In such scenarios, the total number of candidates can be very huge. Now, when you are going to work on such huge candidates, you may not have enough of memory to hold all these combinations for the purpose of analysis or for the purpose of generating frequent item sets. Now, in analytics, that is big data environment, when you want to make use of a priori algorithm, then we should see to that you have enough of memory to handle all possible combinations of candidate sets, or you should have an approach that can address all possible candidate sets, though they are not available in the main memory. Now, when you talk about a single transaction, sometimes a single transaction may contain many candidates. Now, this is also another challenge when we are trying to deal with respect to voluminous database. Now, how these challenges may be addressed? The approach is, when we are dealing with respect to very large number of candidate sets, these candidate item sets, instead of holding them in a flat file system or an environment, you can store them in a hash tree. So, you will have to define a function, hash function, based on the product ID, for example, and then you will have to hash these candidate items into this hash tree. Now, what may be available in this hash tree? The leaf nodes of the hash tree contain a list of item sets and the corresponding counts, that is the leaf nodes, the lowermost nodes in the hash tree. What about the interior node is? The interior node contains the hash table, which is used for traversing or reaching a specific item set. Then you will be having a subset function. This subset function is used for finding all the candidates which is contained in a single transaction. So, your approach must have a methodology for generating this hash tree and also for retrieving information from the hash tree. Let us consider an example of generating candidates. As already mentioned, a priori principle will not consider the subset of items which are not frequent. Let us take a candidate set L3. Assume there are 5 items. These items are 3 item sets. ABC is one frequent 3 item set, ABD, ACD, ACE and BCD or the other 4 3 frequent item sets. Here 3 frequent item sets means there are exactly 3 elements in the given item set. When you join these frequent item sets with itself, then we may generate one possible item set A, B, C, D, that is one possible 4 item set. This A, B, C, D 4 item set is generated by combining A, B, C and ABD item sets respectively. Similarly, you can generate ACDE from combining ABC and then ACE. When you combine ACDE, you may find this ACE, though it is frequent, the ADE combination it is not frequent. Therefore, any set that is generated by involving the combination ADE, which is not part of the frequent item set, then you cannot generate any other subset from this set. So, the combination ACDE, though part of the candidate set, will not be considered for the frequent item set, and hence it will be eliminated. So, this process is called as pruning, and the process of generating k plus 1th item set is called as self joining. So, ultimately the only single item set that will be passed to the next iteration will be A, B, C and D, which is a frequent 4 item set. Now, when you want to compact the output, what is that you need to do? To reduce the number of rules which is going to be the output of a priori algorithm, you will have to define how these frequent item sets are going to be generated. While generating the frequent item sets itself, you must be in a position to understand whether it can be considered for the next iteration or not. So, there are few processing that you can do, and accordingly you can say whether an item set is fit for the following iteration or not. Two such metrics are maximal frequent item set and closed item set. What exactly mean by maximal frequent item set is, suppose there is an item set which is frequent, but you want to consider this to be maximal, means then none of its immediate superset must be frequent, and when it is not going to be frequent, you consider that to be a maximal frequent item set. The second metric is closed item set. When you want something to be considered as a closed item set, none of its immediate superset should have the same count as its set. So, the count must be greater than 0. Now, you can make use of these two metrics for the purpose of understanding items that are not frequent and which may be used for the purpose of further processing. Let us understand this with an example. Consider the item sets A, B, C, AB, AC, BC and ABC respectively. The items, their corresponding support counts are displayed here. Now, can we consider item B to be maximal or not? Here B has a support count 5, but it is not considered to be maximal because its immediate superset BC contains a support count value 3, which is same as the frequent threshold. Therefore, I cannot consider item B to be a maximal item set, but can I consider B as closed item set? Means yes, it can be considered. The reason is its immediate superset, none of its immediate superset. So, the first superset is BC, the second immediate superset is ABC. Both these supersets does not contain the same count value. Therefore, I can consider the single frequent item set B as a closed set. Let us take another example, AB. AB support count is 4. Can AB be considered as maximal? Means yes, of course it can be considered. The reason is none of its immediate superset must be frequent. So, the superset for AB is ABC, the maximal superset is ABC. The support count for ABC is 2, but as per this problem, the minimum support count for identifying an item to be frequent is equal to 3. So, the immediate superset of AB, that is ABC, has a support count 2, which is less than the support count. In other words, this is not frequent. Therefore, the 2 item set AB can be considered as maximal item set. Similarly, can AB be considered as closed? Means yes, because none of its immediate superset must contain the same count. So, the immediate superset of AB is ABC. The count is 2 here and the count is 4 here, both are not same, therefore, I can consider AB as a closed item set also. Now, the purpose of maximal and closed item set metrics are for restricting the number of item sets that is going to be generated and passed to the next phase for the purpose of generating frequent item sets. So, to summarize, in real world, associations between item pairs provide great insight to business and it may be very well used for the purpose of making profit. Major challenge in a priori algorithm is the number of item sets that is going to be generated and used for further iterations to identify frequent item sets, and the challenge need to be addressed by means of monitoring the total number of outputs that is going to be generated. Thank you.